So, the new topic for this session is called JUnit, and I will tell you what is test-driven development, what are unit tests, what is JUnit, unit test framework, what are main parts of it, like test suites, test cases and test fixtures, what are assertions, little bit about mock objects and Mockito testing framework, data-driven testing and testing approaches. So first, if we go through declarations or terms, you should understand there is difference between debugging and testing. Problem is that when you write your code, computer does exactly what you have written in your code, but it happens that you tell computer what it needs to do, not what you want it to do. So computer is something like this hard-working but quite stupid demon which fulfills what you require it to do, not what you wish it to do. And in general, debugging means that if you see that your program in computer works differently as you wish, you have to find out what exactly you told in your code computer to do. And that is debugging, but testing is has more wide scope of figuring things out, and in most cases you want to find out what happens with your code and your implementation, how it works when something goes wrong. And as more complicated your software is, as more things may go wrong, and then you need to test it out, how exactly your implementation, your software deal with these situations, etc. And so you need to do not only debugging, but and also one of computer scientists, I don't know which one, told something like this: if coding is putting bugs into your software, then debugging is taking these bugs out of your code. And because debugging is harder than coding, therefore you never should write code on the limit of your possibilities and your skills and knowledge, because if you write so, you will never have enough skills and knowledge to debug it properly. That means that when you write your code, it always should be as simple as possible, not as complicated as possible. And now about testing. There are two different approaches how you do testing. The more classical approach is that you first write your code and then you test it. And this approach works pretty well when team is small, starting with one person in a team and maybe few more persons in a team. And good thing is that usually such approach is probably more effective, because testing itself, of course, is not productive work in terms of implementing software. In most of cases, your work which is considered productive, which makes income for you or for your company, is implemented features of your product. So you get paid by what your code, your software does. And you are not paid directly by how much you have tested it, etc. So these are management overheads, which are some part of your productive work. So you want to minimize this overhead work. But problem is that when teams become bigger, when software becomes more complicated, then testing later becomes more inefficient, and also coding becomes more inefficient, because when you start working in large team in parallel, one of best ways how to become ineffective is to not know how exactly it should be implemented, how exactly this interaction between your code and some other code, or when it's executed, your part and other part will behave, how it will work. You may make some assumptions, these may be wrong, etc. And then you are into infinite loop of refactoring, redoing, until it starts working together. And if you are in such situation, you can avoid it by starting development tests before actual software. So first, it works better when you need to do different kind of integrations, because then all these assumptions, how exactly it is called, how exactly data are transferred from one place to another, and of course data in object-oriented approach is instances of the classes, or in jargon, objects flowing around and passed through the methods, etc. And also, when you start with writing tests, you also can test out your assumptions about your design, and if it's hard to test, probability is very high, it will be also hard to maintain. And what kind of software is hard to test? When you have these unneeded couplings, when you have unneeded dependencies between sequence of called methods that only in this particular sequence method can be called, when you have dependency between creation of object. To use this object you have to create another object first. To create this another object you need to create yet another object first. So everything is entangled together, and you have to set up a very complicated environment just to test it out. Probability is very high. You will have to set up very complicated environment to use it. And you particularly, for these 2 weeks, you actually are working in test-driven development, because you have tests implemented already, and you need to implement your code that it fulfills requirements of these tests. And therefore, in real world, you can switch your focus and attention from test later development, or test last development, and test driven development, depending on which stage of project you have. If it is very clear what to do, you can start developing and then add tests later to check for regressions. If you do not have enough information how exactly this should be implemented, my recommendation is always start with writing tests, because then you can put these assumptions in tests and you have precise code what you can talk about, for example, to prove to your colleagues that some design assumption is bad, because all this ugliness what you can show in your test shows, for example, how hard it is to use particular API or whatever. And then there are different kind of tests in different stages of your project. During development and debugging, and after that you write so-called unit tests, and unit is the closest test to your code, which means in general single unit is agreed to be one single function or single method. So in these unit tests you check how the single method works, and if it works according to this unit test, you assume that at least at unit level it is okay. But when you have implemented many classes and many methods, then you have to start testing how they interact each to other. Usually for any non-trivial project you have at least few classes and few objects interacting each other. So that means when you call method from one object you have to pass reference to other object or something similar. So you start doing these integration tests, and new problems may arise here, because if everything works correctly independently, when you start testing everything together, you may find out inconsistencies between these assumptions, how exactly it's called, what data are passed, etc. Then you can use system test, where you test entire system. In most of cases these are done from user's perspective if this system has user interface. If it's not, then it is tested from API calls and whatever. And also, we will see this later, we can also automate these user activities as well, that even in system level test you can check this in automated way by emulating user activities. And then before you release this system to your customer, your customer can do acceptance test, where customer reviews and tests your software again from their perspective to check that this system is acceptable. So, and these programmer tests are JUnit tests, unit tests. JUnit is just one framework for them. Unit test in Latvian is vienību tests, and JUnit or unit in Latvian would be one of these frameworks. How can you write these unit tests? So you can create these unit tests to first to test assumptions about your design, if you start with test-driven development, or you write these tests to be sure that this part of implementation never will become worse. Because very important thing for software development is that any change potentially may break entire system. You may want to improve it, but what actually happens, because you didn't think it through very well, you may actually break something. And the biggest problem is that you may not notice that you have broken something until you actually reach some particular functionality. And for such cases, automated unit tests works very well, because after all these changes in your software, you can rerun these unit tests again and check that nothing is broken. And that's the main important aspect of unit tests, that you can always check for regressions and you are not afraid to do some minor or radical changes in your design, because you can always rerun these tests and check that everything still works. And there is one of authors about testing, Michael Feathers, who wrote a book Working Effectively with Legacy Code, and his idea is following: if you do not have automated tests for your software, it immediately becomes legacy code. That means that nobody understands how it works, nobody understands how to change it. You will not understand how it works and how to change it after 1 or 2 weeks when you are done one particular part of this software. And automated tests are good reminders about design, good reminders how this software actually should be used. And what tools are available in Java? Leading automated test frameworks are JUnit and TestNG, and of course, as it's always in Java, there are dozens of other frameworks which are not so popular. If you look on features, then TestNG is more feature-rich, but if you look on availability, then de facto standard is JUnit, and we will also use JUnit because for our modest needs JUnit is feature-rich enough, maybe with some additional libraries and frameworks. And latest stable version of JUnit is version 5, but most of Java developers usually use still some version of JUnit 4, hopefully not older, because there was radical change in releases from JUnit version 3 to version 4, because version 4 introduced Java annotations, which were used in TestNG few years before that, and that was one of the reasons why TestNG became famous and popular, because at that time JUnit version 3 was more rigid, harder to use than TestNG. But starting with JUnit 4, when they introduced annotations, it's still not so feature-rich than TestNG, but it is quite easy to use and quite popular. And best thing is that usually JUnit framework has built-in support for all popular IDEs. And what are main concepts of JUnit? First, you write different kind of test suites, and test suite is Java class which has proper Java annotations inside it. So test suite is actually a container of test case. So usually you write test cases which has test annotations inside it, and if you need, you may have contained them together in test suites which has different annotations. Then you have so-called test fixtures, which allows you to prepare state of your environment with before and before class annotations. And then you have test methods which are annotated with these test annotations. And what is life cycle of these JUnit test cases? First, you may need to prepare something, and if you need to prepare something, then you can choose 2 different approaches. You may have method annotated with either before class or before. And execution and you may annotate with these annotations more than single method if you need, if your environment is very complicated. But when this test case will be run, first all methods with annotation of before class will be executed, and these are static methods. So you can create new instance if you need, etc. Then all methods of before will be called, and these are not static. This means they are independent for each particular test method here, and then one particular test method will be executed. After that, after method will be executed, then before method, another test method, and after method, and then at the very end after class. And in general, each particular of these sequence of events workflows is executed in separate concurrent thread. So that means that if you have to prepare something, you have some dependencies what you need to prepare here for this particular test method to execute. So you need to do all these preparations here in before class or in before methods. And then there are some other annotations like @ignore. You can ignore some particular test method. Here is example of code how simple test case of JUnit framework looks like. So you have quite standard Java class, except you have to import JUnit libraries, and then you have these annotations: before, test, test, ignore, test, etc. And then Java compiler and in Java runtime it will understand that from this import and from these annotations it has to be executed as a JUnit test case. And as you can see, there is no public static void main method, or if it's run in separate thread a start method, it is started somewhere else, and then from JUnit framework your particular methods of this class are executed. And then you can aggregate test cases into test suites. So test suites are like container or bucket for your test cases. Again, starting with JUnit version of 4, everything is managed through the annotation. You import JUnit libraries, and you say with annotation run with suite class, and suite.class means reference to declaration of the JUnit suite. So you run it with this class, which describes how exactly it will be executed, and then you annotate suite classes, and this annotation has additional parameter here as a array, let's say literally declared array, where you have references to these test case classes. And then, because every Java class has to have declaration and body, you also has this class like calculator test suite, but this body can be empty. In your particular case, you have this test suite in here, and in this case it's more complicated because first it runs with customized test suite class, GTM test suite, which extends this class, and also it has body here. In this body there are some public constants declared. And then usually you have to have different kind of assertions. Do not mix JUnit assertions with Java assertions. In JUnit framework, assertions are called methods, static methods, which you call to check that something is equal, true, not null, or whatever. Because without such assertions, only thing you can test it that when you run it, it doesn't throw unexpected exception or throwable, and it doesn't fail in any different way. But it doesn't mean that it will actually work properly. Like if you have simple calculator without assertions, you cannot check that it actually calculates values properly. And particularly for negative tests, there's also assertion assert fail method, which says that if execution of test reached so far, then this test actually failed. And here is another example to check, for example, that there are specific values inside the list of customers, and good practice for these assertion methods is that first argument what you are passing here in this parameter is string, which will be used as a message field for assertion error if this assertion will not be true, if it will not hold these rules. If you are not required, but if you will not add this string as a message field, you will just see assertion error, like expected value is this and actual value is that. And also, if you need to compare two different values, very important thing to remember is that expected value is first, actual value is second. So if you assert just something is true, you will have only one parameter with some statement here, which is either true or false, and if it's false, it will create assertion error with this message field. If you need to compare something, you should have three parameters used all the time. Message for assertion error if it's not equal, and then comparison for these values, expected first, actual second. And then you need to remember that testing means to ensure how it works if something goes wrong. That means you will frequently have so-called negative tests. When you actually try to pass wrong data, you try to break your system and check how it deals with this. And in theory, actually, number of negative tests is always bigger than number of positive tests, because if you do everything right, this is just one very thin pass to do this, and everything else is negative tests. So negative testing is very important business. And how do you test it to pass your JUnit tests? You can do lazy approach. If this negative test throws some kind of throwable, exception or error, then for this test annotation you can add additional parameter expected and then reference to class of this particular throwable. And if such throwable will not be thrown, then this test will fail. But my recommendation is that you always use more complicated approach with try and catch. Because then you can try, at the end of this try you call fail method, because it should fail, and sometime before that this exception or error should be thrown, and then you catch it, and when you caught it, then you can do additional checks for this particular exception, for message field, for precise type, and many other things. Then, when you work with distributed systems, and simplest distributed system is client and server, through the network or from client to the database, you never know for absolutely sure was it very slow or did it actually work. And to not wait in infinite time for very slow. So you may assume that something is very slow, but actually it doesn't work, and you may wait infinite time. And therefore, for such things, when you assume that if something is truly slow, it actually doesn't work, you may add timeouts for your tests. And you may add timeouts in two different ways. You can add timeout for one particular test method. for one particular test annotation, like timeout, and here is number in milliseconds. Or you can add rule for entire test case. And then property for it is a global timeout. You create such variable and you say categorized value for this timeout class, like 2 seconds. And then about dependencies. So in theory, proper way to do, so for example here you have method 1 to test, method 2 to test, and you have some dependencies here that you need to create some data structures here and here and here to do them. In theory, what you always need to do is to prepare all these dependencies and data structures in before class or before methods, and then you can run independently in any order all these actual test methods. But in practice, when I worked in testing business, I find out that such a ceremonial approach is quite inefficient. It is robust, in theory it is good, but in practice it just takes too much of effort. And what I have found out that you may be much more efficient in your testing business, because remember, you usually are paid for implemented features and covering business needs of your customer, not for testing itself. So if you can test more doing less, then it's always great. And therefore, you can do it a little bit differently. You can force order of executed methods with fixed method order annotation, and then you have these test methods, test this, test this, test that. As far as I can tell, these are still executed, looks like in separate threads, but at least, for example, let's do more details here. Here you always will have something like public class test this, and here is body. So when JUnit test actually executes them, remember that this is static and this is static, but these are not. Actually, JUnit creates new instances like test this is new test this, and then it says something like test M1, and then it says test this, new test this, another test, and call M2. So it creates new instances of these test objects to call this local method. So these are static methods belonging to the class, but these are local methods belonging to the object or object methods. So it creates new independent separate objects for each particular execution of this method. And even though you know that execution order will be always M1 and M2, new object is created. And again, if you need some dependencies here between this object and that object, you have to create this static structure, how you exchange these data, that this object can refer to that structure, and this newly created object also can refer to that structure inside the body of the class. Otherwise, it will be executed in proper order, but still something may go wrong because you have created the non-static. For example, here you may exchange information like, say, int count, but if it's not static structure, it belongs to the object, you will have int count for this created object as a separate holder and int count in this object as a separate holder, because JUnit test framework creates new objects for each of these test methods. And in details I will show it for practical exercise. So remember that in general, what is happening, JUnit test frameworks creates new instance, or in jargon, new objects out of this class, and then it executes this before class as a static method, before for each particular object, calls this method, calls after, and after class a static method in concurrent separate threads. If you say fix method order here, it will work in proper order, but still methods themselves will be executed independently with separated data structures. And then little bit about failures. Sooner or later you will get some kind of failures in your test cases, in your test methods. So how does it fail? It fails similarly to unexpected throwables or unexpected exceptions, because a filer object is created and thrown. And here work of these failures is very similar to working with exceptions. So when such failure object is created, it is listened to this listener of failures, execution of test is halted, and this failure object is collected inside of other object, and you can see here it in Eclipse. So what we see here in this test status as a tree here is these objects collected about execution results. And if we have some failures here, then this is this failure object created for this particular test. And so in JUnit framework, then you can collect all these failures and you see what has passed, what has not passed. And I already told you that there are two different kinds of failures. We need to add something for testing here. To see more interesting results. And of course, practical details, how exactly this look in different IDEs is different. So, here we have two different things. First, we may have something red, which means unexpected exception or unexpected throwable in general happened during execution of this test case. Particularly for Eclipse, these are shown in red color, so that means it broke with unexpected exception or error. But in some cases there were not caught any unexpected exceptions or errors, but they got just assertion errors for assertions. So here it is this failure object created, which shows where this unexpected error or exception occurred. But here everything from perspective of exceptions and errors, everything went correctly, but some of assertions failed. So these are assertion errors and these are these failures, or in red color. And of course in different tools it may look differently. And then we also will have this problem in practical exercise with dependencies to external system. Remember that in theory JUnit framework is the best to test single units or single methods, and that's how it should be used in most of cases. But unfortunately some of these single units may depend on quite complicated infrastructure behind it. Typical dependencies are relational databases, other systems working through the network, maybe something stored in persistent, other kind of persistent memory like file system or whatever. And that is big problem for unit testing, because it means you can't test one single unit without all related infrastructure behind it. But fortunately there are other frameworks which are not part of standard Java but we can use, are so-called mock objects. So if you have some method M1 which you need to test, and behind this method you need to have a relational database, let's say that database, then it is actually not unit test anymore, it is integration test. You test this particular method together with the database. You can do it, but remember that this is higher level of testing. It is now actually integration testing when you start testing everything together. But if it's not your intention, you can cut it off and introduce mock object here. And usually you do not need entire database to mock it up. Usually you just need, if your design is sane, to deal with few interactions with this external system. And you mock it up something like, if this thing was called, return this data. If this thing was called, return that data, etc. And leading framework in Java, at least as far as I know, are framework called Mockito, and it works something like this. At first you import as a static structure entire Mockito framework libraries, so it is quite memory consuming, but in most of cases you don't need to care too much about it. And then you declare what exactly you will mock up. In this case we are mocking up a linked list, so we are not creating real linked list, but we are saying that we will mock it up. And then we say when somebody will try to get first element of this linked list, we will return string first. When somebody will try to get the zeroth element, in this case and first element, next case, then we'll throw new runtime exception. And then when we try to use this, here we get string first, here we get runtime exception, and when we try to get other element we get null, because we have not declared what exactly to do in this particular case. And syntax is something like for Mockito, like for functional programming, but that may be a little bit confusing. Then, depending on what exactly you want to do, called methods are a little bit different, but in general, as far as I have worked in different Java projects, that was the best framework I could find. And now about test approaches. Problem with testing is, as I told you, that there are almost infinite possibilities what exactly you can do with your software. For example, you should remember our simple cults, which is very simple calculator which takes two integers and four operations. And to fully test it, how it works, we need to do, starting with minimum of integer minus blah blah blah, minimum of other integer, let's say plus, then minus, then multiplication, then division. And then we increase this by 1, redo it again, then increase this by 1, redo it. When we have reached an end for this, we increase this by 1 and redo it again. So how much possibilities here is? Integer is, I think, 4 bytes long, so it is, let's double check it. So this is size of integers. You have approximately 2 billions of numbers here times 2 billions of numbers here times 4 for 4 operations. So total number of possibilities you need to check for this very simple stupid calculator is 2 by 2 4, by 4 is 16. Let's check. 1, 2, 3, 6. Is it says there? Wait a minute. Nē, jau tā es rēķinu. It is in power of 18. So approximately or 1.6 and 10 of power 19 operations. And you can check how many billions of years you will need to test it out. If you can run, for example, 1000 operations per second. So here I used billions, but I could also use 2.10 in power of 9. And of course it is not practically possible. So what can we do? We can make a number of these tests much smaller by assuming that everything else will be some kind of not important subset of what we actually tested. And what we have to do here to make number of tests much smaller, we can look in our source code, we can draw like block diagram, how decisions are made, where exactly is executed, and we got something like this block diagram here. And we have to cover this path of this block diagram. So here, what does it mean? If branch, it's something like if, and if it's loop, it's something like do or while, etc. So we need to cover all of these branches of block diagrams at least once. And if these are covered at least once, then probability is quite high that we have tested all important aspects of our implementation. And because of branches and loops, there are dependencies that, for example, to cover if and else condition here, we will cover initial part of our implementation more than one time. Similarly for loops, because we need to check, for example, what happens if its loop is executed 0 times or many times. We need to call again. So some of these parts will be covered more than one time, but we should check that everything of our implementation is covered at least once. So that means that all the branches, all conditions, all loops, all interfaces, all invocation paths are covered at least once. So invocation part is a little bit in direction of integration testing. For example, you may see that even in your simple practical exercise, there are dependencies how exactly methods are called or orders of methods. For example, if somebody will start calling like getXML before or validate XML schema, before that maybe something wrong may happen because of these internal dependencies, or from some previous exercise like array filler manager here. Again, assumption is that you call setup first and these other methods after that, and if this method will be called before that method, again probably something wrong will happen. So, and that's what you need to check, and if you do this, then number of possibilities what you need to check is billion times less, because you are testing only these significant differences between particular things. So you are assuming that simple adding this number and that, if it works with these two numbers, will work for other two numbers as well. You check only these significant differences in your code. And then when you do design, other important thing is how can you check your progress and how you report about this and how you design them. And for example, here you have your tested code which need to be tested, and this is list of methods, and maybe actually this is one class, this is another class, this is another class, and here are these methods. So testing particular method would be this one single unit. And in general for your tests you also should have approximately the same relation between tested methods of classes and tested tests. That should be approximately 1-to-1 because of checking progress and reporting. For example, if you will create it design following that you have one test method which tests so many things, and then you have these test methods which check that part, and you will see that this fails and it doesn't fail, you'll say okay, it's almost done for us because we have one failure here but approximately 12 or 10 succeeding tests. But it's not the case, because in this case this one failure is much more important than other because it covers much more functionality inside your classes. And similarly, if everything here fails but this doesn't fail, you may get wrong impression that almost nothing works because you have 10 failing tests and only one test is passing. And so in general that means that numbers and complexity of the tests should be relative to the number and complexity of these tested classes. Otherwise, you never will get good impression about your progress, and particularly about testing you should know something about Pareto principle. Maybe it's with 2T, I do not know. With 1T, Pareto principle. So what this principle says, that in many cases, because of different complexities, for example, here is list of your features, and here is your effort to implement them, and not all features are equal, and usually you will get 80% of features covered with only 20% of code. and then remaining 20% of features will require 80% of code. And such Pareto principle appears everywhere when there is an equal distribution of something like this. For example, network traffic is, according to Pareto rules, that approximately 20% of users generate 80% of traffic, and then 80% of users generate 20% of traffic. Why it happens? Because if you have this unequal distribution, here is this 20% of something which has 80% of some value, and here you have 80% of something which has, okay, it should be something like this 20% of something in value. And everywhere when there is this unequal distribution, Pareto principle applies. And what is funny thing, if this is very seriously unequal distribution, when you look on these remaining 20%, Pareto principle still applies. 80% of remaining 20% will have remaining 20%, and remaining 20% of 20% will have remaining 80% of this 80%. And if you have enough of this complexity going here in infinity, you will see that very, very small fraction of something actually takes very big fraction of here. Pareto rule applies for income distribution or wealth distribution for people, whatever. And that's also important for testing. So do not go into unexperienced developers who do not know this, and unexperienced like students who write their academic work. For them, work is almost always almost done. Why? Because they have done this particular effort, and you see, oh, biggest part is already done. But then to cover remaining part for these complexities and other thing, it takes more and more and more effort. So therefore, to get good measures for your quality assurances, etc., your JUnit tests should somehow reflect complexity of your tested code. If it doesn't reflect this tested code very well, then you always will have this misleading feeling that almost everything is tested, almost everything works correctly. But in practice this may mean that only some easier and smaller part is actually tested and is actually working. Then another problem is for more complicated systems which has persistent memory. And persistent memory means you run this system again, but it already has previous history inside its memory from previous tests, previous executions, etc. And you will have similar case in your practical part, like your persistent memory is relational database. It may be everything else, like XML file or whatever. But problem is that if this memory persists, then your test strongly depends on what is inside this persistent memory. You need to test search. You need to search for particular student or teacher, Jānis Bērziņš, and you can get following results. 0 records are returned because there is no such user or teacher, student or teacher in this database. You may get only 1 record if there is only 1 teacher or student. You may get several if they are namesakes, different persons with the same name and family name or surname. And that means without knowledge about this persistent memory, you actually do not know what is good case, when your test should pass, when your test should fail. And how can you deal with this? Heavyweight approach is that you maintain your own dataset for testing purposes, where you know what is inside your testing dataset, you should avoid this approach as much as possible, because for complicated systems, this maintenance work may be quite a big effort. And instead of maintaining this entire dataset for your testing purposes, you should use this local lightweight approach. When you need to search for some item, first create it. Then, if you created only one, you know that you should search only one such object. If you created two similar things, then you search for them and you know that you should get two similar things. Then you can modify it and then you can delete them. And with this crude approach, create, read, update, delete, if deletion is also possible. Good thing is that when you finish your tests, you actually do not have any changes in your initial dataset here for this persistent memory. So if you will need to work in testing and test automation, remember that you always start with this lightweight approach. You create your own object, you try to search for it, you modify it and you delete it. And you rely on this heavyweight approach on particular dataset in your persistent memory only if for some reasons you cannot do cleanly this lightweight approach. And then dealing about test results, I told you already that complexity of your tests, like number of methods inside these test cases and number of test cases or these test case classes, should be approximately the same as number of your tested classes, because otherwise what you see here in this test result do not really reflect your progress regarding to your project, because if this one thing covers almost everything and these other things covers almost nothing, then you can't just say that, for example, 60% or whatever were implemented and 40% still needs to be implemented. But also you need to remember that systems are complicated, and in ideal world you would write your JUnit tests, you execute them, everything is green, and that means that your program is flawless. There are no any bugs and errors inside it. It may not be the case. In real world it may be that your JUnit tests or unit tests in general are not complete, and even though these tests show everything is green, there are still some bugs hiding inside your software, and this result is called false positive result. You see that everything is nice, but actually something may not be nice because your tests do not catch all possible bugs. Then you may get some negative result because your program is faulty, so that would be just negative result. But because there may be problems hiding in unit tests themselves, you may also get errors, not because tested program is faulty, but tests themselves are faulty, and this is called false negative result. So it looks like negative, but it's actually not negative, it's false negative because there are bugs hiding inside tests themselves. And now again, this Pareto principle is applicable to distribution of false positives and false negatives. For positive and negative result, real positive result and real negative result, this is more or less equally distributed or linearly distributed regarding to your test coverage. So in x-axis here is test coverage, 0 means nothing is tested and nothing is covered, 100% means everything is tested and everything is covered in terms of these things: all branches, all conditions, all loops, all interfaces, all invocation paths, not in terms of this 10 in power of 19 for our very simple calculator. So as more and more things you cover, and here is unknown number, hopefully big number, at least few hundreds, at least something about 100, or maybe better, bigger, is number of these failures or passes. So if your coverage becomes bigger and bigger and bigger, you have more and more real positive results when everything is green. Of course, sooner or later you will catch some negative results, and negative results will be much smaller if you do test later development or test last development. It will actually be everything is red if you will start with test first development, and then you change number of negative results to positive when you will start implementing it gradually. But then there are number of these false positive. Actually, this should be probably much smaller, not here, but somewhere here. But because here this number is not mentioned here, it's just qualitative result, not quantitative. Number of false positive do not decrease linearly because of these internal complexities and dependencies. Number of false positives do not decrease initially and then decrease quite sharply somewhere at the end. And false negatives initially, when you start with simpler areas, etc., when you are here, the work is almost done, then number of false negatives do not increase very dramatically. But when you are in this muddy area of edge cases and internal complexities, the number of false negatives increases dramatically. And that means there is somewhere this spot, according to Pareto principle, it would be somewhere in 80% of coverage. But in reality, this distribution is much unequal than in normal Pareto distributions. Usually it's somewhere around 90, 95, 99% of coverage, when probability of false negatives increases dramatically and probability of false positives decreases dramatically, and so you stop your testing coverage somewhere around here. Because if you will want to get better coverage, you will spend much more effort dealing with these false negative results, and so you will need to do much more work without much bigger benefits for your testing results. And that's it in short about testing, test automation and JUnit testing framework particularly. Do you have any questions or comments now?